Here I will show a couple of demos of things we've done in the 5G, 6G Innovation Testbed. The first is a network resiliency demo where we do a denial of service attack on the network and use an orchestration tool to keep the network stable while using a threat detection tool to shut down the attack. So first we use the AMCOP orchestrator to orchestrate the 5G core. When we go into the testbed user interface, we connect the G node B and we'll just confirm in Grafana that it's connected. Then we'll go back to the user interface and register some UEs to the network. In this case, 6 UEs just to set a baseline of traffic. Now, if we go into NIKSUN's net mobility monitoring software, it says that traffic is normal, just those 6 UEs. But when we initiate the denial of service attack and go back, we have an alert, a high number of NGAP messages. Now, first, if we go and look at AMCOP, we'll see that AMCOP has already scaled up the network to protect users. Meanwhile, the traffic storm, the denial of service attack is mitigated. And when we go back to AMCOP and Kubernetes, we see it has scaled down the network. Now, the great thing about this scenario is we see that the time and duration of the attack was very short because the net mobility monitoring software recognized it, mitigated the attack, and took care of it. But at the same time, right when the attack happened, the orchestration tool enabled by AMCOP scaled up the network to make sure that those 6 UEs didn't get denial of service, that they maintained service on the network. And as soon as the attack was shut down, AMCOP also recognized that the threat was gone, that traffic was back to normal, and it could scale down the network so that we weren't overusing resources or wasting money. And so this is a very nice demonstration of not just attack detection and mitigation, but also multi-cluster orchestration, closed-loop automation, and lifecycle management. Okay, in this demo we are going to look at dynamic quality of service modification that's enabled by the CAMARA project. And we'll stream a video through the network and then create congestion in the network that degrades the quality of the video. But we'll use an API to modify the DSCP value, and that will improve the quality of the video. So this is the video streaming without congestion. And if we look in Wireshark, there's no special marking done on the packets. But then if we go and use a tool called iPerf3 that we've enabled in the testbed, it will create congestion and the quality of the video suffers. Okay, now then we can go and use an API created and enabled by the CAMARA project, and in the testbed UI we can configure the DSCP rules that the API has set. And when we play the video with congestion, the quality improves, and we can look in Wireshark to see exactly where the packets were modified to make the video look better. So this is a side-by-side comparison. This is before congestion, this is during congestion but without any special marking, and this is with congestion but also with the API doing its work to tell the network that the streaming video user needs to get better quality of service assigned to it. And you'll really see that the two on the top are very hard to tell the difference between, whereas the one on the bottom lags behind, is lower quality, and generally looks bad. And so it's a nice simple demonstration, but a nice demonstration to show how you can use tools like APIs to teach the network how to treat certain users over others when maintaining quality of service. And it's just one of many tools that our users can take advantage of in the IEEE testbed to do scenarios or use cases like this one.